So I have posted more of the lecture notes from now the previous 3 days worth of lecture notes are available on Sakai, and all but the first lecture should be available as YouTube videos. So currently, I think you have a pretty good access to my lectures in various formats. I have a question that I'd like to ask you, which is, oh man, my dot cam is looking kind of weak today. My question is, how are the homeworks going? Do you feel as though the homeworks are too small or too large, or have I successfully changed the work required so that you don't have that kind of painful need to show your work? How are the homeworks going right now?
For me, it's pretty good.
Yeah.
Yeah.
They're reasonably good?
I've noticed the most recent one that you just posted this morning, it wasn't like, it was a bit more than what we covered yesterday. Yeah, so I guess sometimes that throws me off when I'm like, okay, this should be yesterday's homework, but it's more than we did yesterday.
Yeah, that definitely occurs. Okay, but beyond that, it seems okay right now. So there don't seem to be a huge number of problems that I can choose from. So I'm like trying to make sure that you have a good coverage on the types of problems that I might ask you on exams. But it's kind of frustrating that I don't feel as though there are many problems that I can ask you via the online format. So I would definitely encourage you, if you find yourself with extra time after finishing the homework, to go through the problems in the book and make sure that there's not some area that I discussed in class, but that you've got no homework on and that you feel uncomfortable with. That's something that I encourage. Okay, yes, I should discuss now the test, which is coming up. So today I will discuss, a discussion of 2.6, which is exact differential equations, EQ. And I'll also do a discussion of 2.8, which is the existence and uniqueness. For nonlinear. But I won't be testing you on 2.8, and I probably won't even give you homework. Maybe I'll give you like one homework problem in 2.8, but really I just want to kind of chat about it. The ideas that are involved in 2.8 are beyond what we can really handle in this class, but I think it's valuable to kind of see what's out there. I just don't want to hold you responsible for the material in 2.8, really. So it's kind of salutary. I'm going to go over it for your mathematical health, but I'm not going to be demanding that you know all the content of 2.8. So with that in mind, the test will cover the following sections, and it'll be only in so the material in chapter 1, which was really just an introduction. So I would say it's probably not very valuable to go back to chapter 1, except to remember some facts about the classification. So things to recall. Solutions, what does it mean to be a solution? And classification. Probably these are the things that are most strongly harped on in chapter 1. So it might be valuable to go back, especially for the classification. Make sure that you understand what the different words in the classification mean and things like that. But mainly we'll focus on chapter 2. So chapter 2.1, which is first order linear. So first order linear and integrating factors. 2.2, which is separable. 2.3, we did a little bit of. This is modeling. Essentially, this is just saying be familiar with some of these different models and be able to write down differential equations according to like a word problem that I give you. Try to comfortable with writing down a diffie-q. Right, most of our work in this class is you're handed a differential equation and asked to solve it, but you should also be comfortable with being given a problem and writing down something. And then 2.4 is existence uniqueness. 2.5, autonomous. And then 2.6, which is exact. This is all of the material that we're going to cover in chapter 6, or I mean in chapter 2. So I won't go over 2.7, which is numerical approximations. I'll discuss 2.8, but I won't hold you responsible for that material at any point, really. What you need from that material is written down in 2.4. And I also won't be discussing 2.9, which is first order difference equations. So on Monday we don't have class. Is that correct? Can someone confirm? Monday we do not have class because it's Memorial or Labor Day.
Yeah.
Sometimes the homework, oh, I'm just reading the comments really briefly. Really tedious. I imagine that sometimes the calculation in the homeworks is kind of painful. So I think that that's a valid point. I don't have any older practice exams, and I am not sure that I'll write an exam that will be identical to some other practice exam. So I don't know if I have a very good collection of practice exams I can share, but I would say that I think it's a good policy to look at problems similar to the problems asked in the book. All of the problems that I've had you do during class are problems from the book, and all of your homework is based on book problems. So I'm going to try to ask you similar problems on the exams. In that sense, previous practice exams could even lead you astray because they're using different books with different topic orderings and stuff like that. Okay, so yeah, basically the idea is by the end of today, we will have covered all of this stuff. And additionally, I'll have talked about 2.8, but you don't need it for the exam. And this will be all that we do with chapter 2. On Tuesday, we'll start chapter 3.
And the exam's on Wednesday, right?
The exam is on Wednesday. I have been promising you to send out an email with the details on the exam since Wednesday, and I haven't done it yet, but I will do it today. Third time's a charm. Any further questions?
Yeah, so I just am wondering about how relevant or how much we should study, like, I don't really have any other better way to say it other than like random obscure things, because there was one question on the homework that I got wrong because I didn't utilize some trig identity, that it like wanted it in that form or something. Is that something we need to be concerned about?
Not really. On my exams, I'm not trying to trick you or fool you, and I'm not trying to test you on ancient calculus that you learned maybe many years ago. The focus of this class, I mean, I'm going to be testing you on the techniques that we're introducing. So the things that I keep on going back to are, how do we solve first order linear? Well, we solve them using integrating factors. How did we solve all these autonomous looking equations? We solve them using partial fraction decomposition. So you definitely know you want to remember partial fraction decomposition. You have to know what it means to be a solution to a differential equation. You have to know how to draw a slope field, how to find equilibrium solutions, how to analyze different regimes where the solutions do one thing in one area and do something else in another area. Those are the things that I'm going to be focusing on.
Okay, thank you.
Yeah, it's not in my interest to make some really hard, like Calc 2 style integration tricks. Any further questions? Okay, so let's get started on our discussion today. Lovely Friday. So we are hanging out in section 2.6, which is exact differential equations. And I'll have some comments about this later, but here is the basic point. So a general first order linear, sorry, not linear, general first order differential equation. So general first order differential equation can be written as m of xy plus n of xy y prime is equal to 0. Okay, so this is kind of a very general statement. And actually, technically, we're not getting all first order differential equations. There are some other ones where I could like do y prime squared or something like that. But we're not thinking about that right now. So I have a couple questions. First of all, what would it mean? What conditions should I put on m and n if this is supposed to be separable?
M should be a function of just x and n should be a function of just y.
Exactly. Separable is m of x and n of y. Good. What conditions should I put so that this is linear? It's kind of a tricky one. What condition should I put on n so that this is linear?
It should be a function of just x or a constant.
Yes, exactly. And a constant is technically a function of x too. So for linear, we require n to be a function just of x, not of y, and m should be linear in y. In other words, if I wanted this whole equation to be linear, a viable thing would be to have like cosine of x times y, or exponential of x plus x times y. But what I couldn't have is something involving y squareds or cosines of y or e to the y in here. So if m is linear in y, then this whole equation will be what's called a linear first order differential equation. Okay, and now we're going to come to another condition that we can place on m and n such that we can actually concretely solve this differential equation. And we will call this exactness. So exactness for us, not just for us, exactness is if there exists a function psi of x and y such that, can someone remind me? Well, maybe I'll say the first one. M of xy should be equal to the partial derivative with respect to x of psi of xy. And what condition should I ask of n?
The partial with respect to y.
Exactly. And n of xy should be equal to the partial with respect to y of psi of xy. So this is another condition that on the functions m and n that allows us to fully solve the differential equation concretely. Okay, and the reason why this works is that if m of xy plus n of xy y prime is equal to 0 can be written like this, is exact, then we just substitute. We write that this is the same thing as partial with respect to x of psi of xy plus partial with respect to y of psi of xy times y prime is equal to 0. Question, if we assume, since we're looking for a solution y of x, if we assume y is a function of x, then what does this term look like?
Chain rule?
This looks like a chain rule, exactly. Looks like a chain rule. So, if this is a chain rule, then let's actually write it as one. Then this whole thing becomes, via the chain rule, so via chain rule, partial with respect to x of mxy plus partial with respect to y of nxy dy over dx equals 0 becomes d over dx of psi of xy. Actually, I should probably put partial with respect to x of psi of xy is equal to 0, because when we apply the chain rule to this derivative, first we're going to take the partial of this with respect to, oh, I'm sorry, I've written this wrong. This is partial of psi of xy plus partial of psi of xy. Right, so here we're taking the partial derivative with respect to x times dx over dx, which is 1, plus partial of this function with respect to y times dy over dx, which is what we get here. This now looks horribly messy, but is this acceptable? Or should I rewrite what I'm doing here?
I think it looks good.
I'm flattered. You're all lying, but that's fine. As long as you understand what I'm doing, that's sufficient. So as long as we can find a function which satisfies these conditions, then we can write this whole differential equation as the derivative of this function with respect to x is equal to 0, and then we can take antiderivatives.
Is that the partial of x?
I'm trying to remember whether I should write here the absolute derivative with respect to x or just the partial. Probably I should write the absolute derivative with respect to x, d over dx of psi of xy, because we're assuming that y is a function of x, so that this function psi eventually can be totally written in terms of x's. And so then this is equal to 0. And then we take antiderivatives. With respect to x. What's the antiderivative of this side with respect to x?
Just psi of xy?
Yep. So we just get psi of xy. What should we not forget?
Plus c.
Plus a constant is equal to 0. So, just like in some previous situations, in fact, in almost all of the nonlinear situations that we come across, we don't get a literal function, right? I haven't been able to write y of x is equal to blah in terms of x, but I do have some equation involving x and y such that any y of x that satisfies this equation is locally a solution. So this implicitly defines solutions. And as we have learned over the past week and a half, oftentimes an implicitly defined solution is about as far as we can get, right? And it's sufficient. Any questions on this kind of chain of reasoning?
Yeah, okay, so I might be jumping the gun a little bit here, but on the homework, I believe it was whatever the most recent one was, there was an example where it wanted us to write the equation in terms of C. So is that, I guess I'm a little confused. Are we saying that psi of x, y, are we saying that it's equal to C?
Yeah, I can subtract c from both sides and get psi of xy is equal to negative c for some constant. And then, you know, since changing, like, this is just a constant. So I can also write psi of xy is equal to some different constant c.
Right, okay,
That's totally fine.
okay, thank you.
Yeah, sure. Okay, so let me show you again why this generalizes. This is a strict generalization of separable. And here's the idea. Let's say that I give you m of x plus n of y, y prime is equal to 0. Now my question for you is, can we find psi of xy such that the partial with respect to x of psi of xy is equal to m of x, and the partial with respect to y of psi of xy is equal to n of y?
But if m of x is, I'm trying to think of how to say this. If both of parts of the psi are just x and y separately, then it would work out. That didn't make sense.
Yes, yes. I think that you're saying pretty much exactly what is going on here, is that we can brute force build psi from this information. Namely, psi of xy being equal to the derivative. Let's say that we have some initial condition floating around somewhere. So I'm going to have x0 up to x of m of z dz plus the definite integral from y0 up to y of n of z dz. What happens when I take the derivative of this function with respect to x?
You just get m of x.
Exactly. This depends on y, so this will go away, and I just am left with m of x. And then if I take the partial with respect to y, then this all goes away, and I am left with n of y. So when m is only a function of x and n is only a function of y, we can use the fundamental theorem of calculus to build psi of xy. We don't have to go looking for it and trying out different things. We can just make a psi that works.
Do you have to add a constant to this equation, to the psi?
Yeah, the plus c will make it so that we satisfy some initial condition. Remember, so those are the two parts. If you want to solve an IVP, you need to satisfy the differential equation, and you need to satisfy the initial condition. If we forget about the c, then we'll satisfy the differential equation, and then we have to add the c so that solutions actually satisfy the initial data as well. So you're right. Yes, we should remember the c.
Thank you.
Okay, so don't forget how to solve separable differential equations, but do remember that knowing exact is stronger than knowing separable. Okay, let's do an example. By let's, I mean I already did it, so it's your turn. Please solve the diffie-q which demands that 3x squared minus 2xy plus 2 plus 6y squared minus x squared plus 3 times y prime is equal to 0. And by solve here, what I really mean is find an equation which implicitly defines solutions. And here, notice that I'm not specifying an IVP. I'm not specifying any initial data. So you shouldn't expect a unique solution. You should expect families of solutions. No questions? Has anyone found a solution?
Oh yeah, I have.
Okay, cool. I'll wait another minute or so, but good. Thank you. Has anyone else found a solution?
I think so.
Cool. Ooh, actually, I could probably do something clever and say like, raise your hand in the Zoom if you found a solution or something like that. I don't need to do that. That's not too. important, but there probably are ways for me to assess how many people are done with the problem. Wait, oh, here's a question. Can everyone see whose hands are raised, or can only I see whose hands are raised?
Everyone can see.
Everyone can see? Okay. Okay, maybe I'll go over this, or someone who has solved this could give me the answer that they found. Maybe I'll go over it so that at least we can see a technique. So here is an approach to solving this problem. What we want to find is we want to find some function psi such that the partial derivative with respect to x is this function, and the partial derivative with respect to y is this function. So a perfectly valid idea would be to take either one of these functions, let's say this function, and try to take the antiderivative of this function with respect to x, and then add on some constant function of y. So my approach is a candidate for psi of xy is the antiderivative with respect to x of this chunk, 3x squared minus 2xy plus 2. So the antiderivative here is going to be x cubed minus x squared y plus 2x plus some function h of y, right? If I take the partial derivative of this function with respect to x, then I'll indeed get 3x squared minus 2xy plus 2, and then this h of y term will totally vanish, right, when I take the partial with respect to x. And now I've kind of gone up by taking the antiderivative with respect to x, and I want to see, can I find a function h of y such that when I take the partial derivative with respect to y, I get this. So if I take the partial derivative with respect to y of this function, so kind of gone up and now I'm going down, antiderivative with respect to x, and now partial with respect to y, here I get negative x squared plus h of y prime, right? So I see that in order for this thing to be equal to what I have here, I need h prime of y to be 6y squared plus 3. So h prime of y is equal to 6y squared plus 3. And so my overall function, the solution that I can write here is x cubed minus x squared y plus 2x plus 3y cubed plus 3y is equal to c, right? And essentially I've just found that if h prime of y is equal to this thing, I just took the antiderivative. So I got a 3y, sorry, should this be a 2y cubed?
Yeah, that's right.
2y cubed plus 3y is equal to c. And then this gives me an implicit, so implicitly defines solutions. So I hope that you remember this technique or this pattern from Calculus 3. Is this kind of something that you remember doing?
Yeah.
Yeah, good. Okay. Let's do another example. Try to solve 2x plus 4y plus 2x minus 2y, y prime, is equal to 0. Any comments on this one?
It's not exact.
Yeah, very good. This differential equation is simply not exact. There is no possible psi such that the partial with respect to x is this function and the partial with respect to y is this function. And you can kind of see that by attempting to do the same technique that I just did. The most general form of function whose partial derivative with respect to x is this is going to be x squared plus 4xy plus some function of y. This is the most general possible antiderivative with respect to x of this function. And then when I take the derivative here, I get 4x, so partial with respect to y of this thing is going to be 4x plus f prime of y, or partial with respect to y of f of y. And I'm never going to be able to recover anything in terms of x from this function. And this function can never look like this one, because here I have a 4x and here I have a 2x. These could never be equal. Not be equal. So this just goes to show, it's important that this is remembered, that not all differential equations are exact. We can't always find functions that satisfy the conditions that we ask. Any questions on this example?
To check the exactness, can't you take the partial of the m term with respect to y and the partial of the n term with respect to x?
Exactly, and that's what we're about to do. So question is, when, or is there a test for a differential equation being exact? And the answer is more or less yes. So let's write this theorem that we're going to prove. Let m of y and n of x be continuous in a rectangular region alpha is less than x is less than beta, and gamma is less than y is less than delta. Then m of xy plus n of xy dy over dx is equal to 0 is exact if and only if m of y, xy, and here I'm using this to denote the partial derivative of m with respect to y, is equal to n of x, xy, on R.
Are you able to move the paper up a bit?
Oh, sorry about that. Yep. Any questions on this? I'm going to discuss this. I'm going to prove it, and I'm going to give some remarks. But just on the statement of the theorem, does anyone have a question?
I don't understand why you're taking the partial of y for m and x for n and not the other way around.
So essentially, I think that should be explained in the proof when I do the proof. But if I take the partial with respect to x of m, then that's the same thing as, let's imagine that there is some psi, such that m is the partial with respect to x. If there is some psi, and then if I take the partial with respect to x of m, then this would be the second partial of psi with respect to x. And this would be, if there was a y here, this would be the second partial with respect to y of psi. Do you agree?
I'm still kind of lost.
So you're assume that psi exists. Okay, for the moment. So we know that m of xy is equal to psi of x, xy, right? And n of xy is equal to psi of y, xy. Do you agree with this so far?
Yeah.
If you want me to take the partial with respect to x of m, then that's the same thing as, so mx of xy is equal to partial with respect to x of psi of x, xy, which is the same thing as the second partial of psi.
Okay, I see that now, yeah.
And then if I took y, if I took a partial with respect to y of n, then that would be the second partial with respect to y of psi. But
Right.
But those two things don't need to have anything to do with each other. There doesn't need to be any relationship between the second partials of x and the second partials of y. But yes, Tate, exactly correct. We know by Clairaut's theorem that the mixed partials ought to be equal. That is, the partial with respect to x, partial with respect to y of psi of xy equals partial with respect to y, partial with respect to x of psi of xy. As long as all are continuous. So indeed, this is one half of the proof. If a psi does exist, then we must have these two things be equal by Clairaut's theorem, but that's exactly the condition that these two be the same. This is exactly
Right, that makes
Clairaut's
sense.
theorem.
Okay.
Yep, and that'll be one chunk of the proof. Very good. Okay.
Wait, what does that symbol mean where it says like on R?
These are two functions. I'm only demanding that these be the same function on my rectangle R.
Oh, okay, gotcha.
Any other questions? Okay, I'm about to make a remark that you don't have to take too seriously because it is beyond the scope of this class, but I think it's still an important piece of this puzzle. And the sooner that you hear about it, maybe the better. So technically, there are two different ideas here. The first is exactness. And for something to be exact, that's precisely exists a psi such that psi of x is equal to m and psi of y is equal to m. So this is what we use in our definition of exactness. And then the second feature that we actually just discussed, does anyone know the name for it? You want to impress me? But probably you've never heard this name, so it's a long shot. I'll just say it. This is closed. So really these are things about differential forms, but differential forms can be written as differential equations. So a differential form is closed if the partial with respect to y of m is equal to the partial with respect to x of m. And now I want to mention an important fact. The region R plays a really important role here. Rectangles have the property that closed is the same thing as exact. So in other words, what we're doing here, when someone suggested, can't we check if it's exact by taking these partial derivatives and checking that they're equal? Technically, what we're doing there is if you take partial derivatives of m and n, you're checking whether or not the differential equation is closed, and then you use the theorem that on rectangles, closed is the same thing as exact. But I want to point out a really significant warning, is that for more interesting regions, closed need not be exact. In particular, if you're looking at an annulus like this, say this is your region R, then here there exist closed forms, closed differential equations, which are not exact. And this is part of a really interesting and beautiful story about kind of the geometry of the regions that you're considering. And so the hints of where this goes are found in your Calc 3 textbooks when you're discussing Stokes' theorem or Green's theorem. And there are all these things coming up about, is your region simply connected, or does your region have holes, and how that changes the answers when you take integrals over things. So I just want to kind of expose some deeper ideas, which is that what we're checking when we take partial derivatives is we're checking whether or not the differential equation is closed, and on rectangular regions, closed is the same as exact. Any questions on this? Okay. This is just a remark that is important to me, and if you continue on doing some mathematics, this idea becomes really, really important. It goes under the name of cohomology, but I've said too much already. So let's discuss the proof of the theorem. So first we show if psi exists, then n of y, or sorry, n of x, xy, is equal to m of y, xy. And this is exactly Clairaut's theorem. Very good. So this was just the discussion we had over here. If there exists a psi that has this property, then, and all these functions are continuous, we need m, n, m of y, and n of y to be continuous on this rectangle, then Clairaut's theorem says that the mixed partials are equal, which implies this holds. Okay. Now let's go in the other direction. So assume that m of y is equal to n of x. Now we need to build a candidate for psi, right? This is just like what we were doing when we were literally trying to find a psi. How do we build a candidate? Over here. What did we try first when we were trying to either work out whether this was exact or whether the other example was exact?
Integrate in terms of x.
Yeah. A perfectly viable strategy is to take m and take the antiderivative with respect to x. So what I'm going to write is I'm going to write a candidate for psi is, well, let's take the antiderivative from x0 up to x of m of s comma y ds plus some function h of y. It's exactly what we did in the previous case, and we can check that the partial derivative of this function with respect to x is what? What's the partial derivative of psi as written here with respect to x?
M.
Yeah, the partial derivative of this function with respect to x is just m of xy. This will go away, and we use the first fundamental theorem of calculus here. Okay, so now the real question is, can we ensure that the partial derivative of this function with respect to y is equal to n? So we want partial with respect to y of x0 up to x m sy ds plus hy is equal to n of xy. If we could finagle an h such that this holds, we'd be done. Okay, so are we okay with this proposition that if we have this, then we'd be done?
Yes.
Great. So what I'm going to write is as follows. We can write the partial derivative. It's actually the full derivative, but partial derivative with respect to y of h of y is then equal to n of xy, and then here minus the partial with respect to y of this ugly thing, x0 up to x of m of sy ds. Right, I'm just rewriting this equation so that I've got my partial with respect to y on one side. Are we okay with this, what I've done here?
Yes.
Okay. So here's the following claim. Claim, this right-hand side looks like it's a function of x and y, right? N is some function of x and y, and this thing is some function of x and y. My claim is that, actually, the right-hand side of this equation doesn't depend on x. It is only a function of y. And what is a way to find out that a function doesn't depend on a variable?
If you get 0 with
Yes, when you take the derivative, you expect to get 0. If a function does depend on x, then when you take the derivative with respect to x, you expect a non-zero function. So to check this, take partial derivatives with respect to x. So I'm going to take the partial with respect to x of n of xy minus the partial with respect to x of the partial with respect to y of x naught up to x m of sy ds. What can I do by the assumption that everything is continuous? I'd like to change the order of these. We can change the order of partial derivatives when all of the involved partial derivatives are continuous. This is basically like a version of Clairaut's theorem. So this is going to be equal to partial with respect to x of n of xy minus partial with respect to y, partial with respect to x of this thing, x0 up to x m of sy ds, by our continuity assumptions. On m of y and n of x. And what is this? What's the partial derivative of this function with respect to x?
Just m of xy.
Exactly. This is equal to partial with respect to x of n of xy minus partial with respect to y of m of xy. What did we assume at the beginning of this problem?
they'd be equal.
Exactly. This is n of x, xy, minus m of y, xy, which is equal to 0 by assumption. So in other words, this whole function, this right-hand side, is just some complicated function of y. Thus, partial with respect to y of h of y is equal to, I'll just write g of y, some function only depending on y. And then we can build an h of y which satisfies the right thing just by taking antiderivatives. So h of y is going to be equal to the antiderivative from y0 up to y of g of z dz. We build the h of y required. Oh, you can't see it. Okay, this is kind of an interesting proof strategy. So let me kind of go over it again. What we did is that we assumed that the partial derivative of y, or the partial derivative with respect to y of n is equal to the partial derivative with respect to x of n. We built a candidate for psi, and it looked like this. And in order for this candidate to actually work, we needed to define some function h of y such that the partial derivative of h of y with respect to h satisfied this thing. This looks like an ugly differential equation because it involves x's and y's, but we actually showed that our assumption that we made at the beginning of the problem implies that this function doesn't depend on x. It only depends on y. And when we have a function that only depends on y, we're back in the calculus situation. We're not in the differential equation situation. We're in the calculus situation where we can just straight up produce an antiderivative using the fundamental theorem of calculus. And so we produced an h of y that satisfies the required property here. And if we produce that h of y, that means that we have produced the correct psi. So our differential equation is exact. We built the psi that works. It's kind of a complicated, well, not complicated, but it's not the shortest proof that you've ever seen, and it has kind of several interesting steps. So this is the proof for why that works. Any questions on this? I wish that I had access to big chalkboards so that this whole proof could be displayed at one time, you know. Anyone have any comment or question or something after I just did all this math?
All good.
All good? Okay. So with that knowledge, let's do some exercises. Exercises. Find b such that the differential equation is exact. And then solve. So let's do xy squared plus b x squared y plus x plus y times x squared y prime is equal to 0. This is a plus. What I mean is find the b such that this differential equation is exact, plug in that value for b, and then find psi.
Is that x plus y times x squared in front of?
Yes, x plus y times x squared in front of the y prime. So have people found the value of b for which this is a closed differential equation?
Mm-hmm.
No.
Can someone tell me what they found for b?
I got 3.
Does everyone agree? Or I'll give you a couple minutes, but hopefully. And has anyone found the value, the function psi, such that this thing is exact?
We'll need a few more seconds.
Sure.
I have something, but I'm insecure.
Let's give it a shot.
I got c equals x squared y squared divided by 2 plus x cubed y.
Well, what we can do is we can check, right, by taking derivatives. If we take the partial derivative with respect to x, we get xy squared plus 3x squared y. And then if we take the partial with respect to y, we get x squared y plus x cubed. And that's exactly what we have here, right? X squared y plus x cubed. So, yay. This is my psi of xy is equal to 0, or is equal to c. In particular, d over dx of psi of xy is equal to 0 is what we had here. And then psi of xy being equal to c will give us our implicitly defined solutions. Any questions? Anyone curious about this or had a different answer or anything like that?
No, I got the same thing. Makes sense.
Cool. So this is all good. This is good material. I like this. So let's come to the next topic in this section, which is almost all differential equations are not closed. This is just a sad fact of life. If you write down an arbitrary function of xy and call that m, you write down an arbitrary function of xy and call that n, the chances are extremely low that their partials agree, right? But there's an idea. Maybe there exists an integrating factor, mu of xy, such that m of xy plus n of xy dy over dx equals 0 is not closed. Right? Like if I come across a random differential equation that looks like this, and I say, I wonder if you're closed, and you take the partial derivatives, and it's like, oh, it's not closed. Well, are you totally stuck? Not quite. Maybe there exists an integrating factor such that mu of xy, m of xy, plus mu of xy, n of xy, dy over dx equals 0 is closed. Maybe there is. So this is just the exact same idea when we were dealing with first order linear. We were saying, well, it's not necessarily the case that the derivative of this polynomial is equal to this polynomial, but in a rather large number of cases, when we multiply by an integrating factor, it ends up working. So we can try the exact same thing here. What are the conditions that we require now such that this new differential equation is closed?
Need continuity on the rectangle.
Yep, we need continuity of mu m, mu n, mu m y, and mu n x, right? All these things need to be continuous. And what do we need for this to be closed? By definition. What does it mean for a differential equation to be closed?
Um of y, or um's of y and unx need to be equal.
Not quite. What we need to do is, this is our new m prime, this is our new n prime, and it's these things whose partials need to be equal, right? So partial with respect to y of mu of xy, m of xy, needs to be equal to partial with respect to x of mu of xy, n of xy. Do you agree that this is the definition of what it would mean for this differential equation to be closed?
Yeah.
Yeah. And so in particular, we're going to have to do a product rule. So really what we're saying is, if I write in shorthand, I need mu of y times m plus mu times m of y to be equal to mu of x times n plus mu times n of x. And the point is, okay, it's great that we can try to wonder when an integrating factor exists, and it's fine for us to try to say, well, if an integrating factor exists, then this thing must be satisfied. The issue is that this is a disastrous differential equation to try to satisfy. So finding mu such that this thing holds, this holds, is more or less very difficult. Like, we've replaced our original differential equation that we wanted to solve by a possibly even more complicated differential equation that we're trying to solve, trying to find some function mu of xy such that it satisfies this horrendous differential equation, right? That's kind of a disaster. You can't even see what disaster is, but here it is. Finding a mu such that all this is satisfied could be just impossible, actually impossible just to do. So the point is, to make our lives easier, what could we do? We could ask, when the integrating factor mu of xy, which works, which makes our equation closed, is only a function of x. And this is really something that you'll kind of see over and over in this differential equation story, is that the full problem is just impossible. And so people, these old mathematicians in the 1700s and 1800s, made these like colossal things. Like, in general, I can't say anything about mu. I probably can't find anything about mu. So the only thing that we can really figure out is, what if by some miracle, the correct mu only depended on x? Can we figure out something about that? And the answer is yes. So like the problem is this big, and then these mathematicians are like, I have a solution in this like tiny little part of the problem, this tiny miniature little chunk I can solve. Okay, so we can determine conditions for when mu depends only on x. If mu only depends on x, then what changes in this equation?
First term would be 0.
First term goes to 0, exactly. If mu is equal to mu of x, then mu of y is equal to 0, and thus the equation that we're trying to solve is mu of, mu times m of y is equal to mu of x n plus mu times n of x. And it turns out that we can actually simplify this out, or we can solve for mu of x being equal to mu times m of y minus n of x all over n. Okay. If this function, so comment, so if we assume that mu of x only depends on x, then this is the differential equation that mu must satisfy. Additional note. If m of y, move the paper up. If m of y minus n of x all over n is a function of x, then we get mu of x, which is equal to d mu over dx being equal to mu times some function which I'll call f of x.
Sorry, could you leave it up again?
Oh, I am just blazing through the page. What kind of differential equation is this?
Separable.
This is separable. We can solve this. So what time is it? How are we doing on time? Oh, we got only 10 minutes left. I always go slower than I think I will. Okay. There are some important notes that I want to kind of comment to you. So the first is, we started this discussion by saying not everything is closed. So a naive but reasonable thing to do is say, is there some function that we could multiply everything by such that this thing is closed? And the answer is, to figure out what such a mu would be practically impossible. So then we made two sweeping restrictions where we drastically cut down on the number of problems that we are trying to solve. Then we said, if I demand that mu of x only depends on x, then first of all, mu of y will be 0. And then this partial derivative will only depend on x, this function. And then if we make that sweeping assumption that mu of x only depends on x, then this whole thing becomes a separable differential equation. And then I can actually solve for mu. So in some tiny, tiny fragment of all of the possible differential equations you can see, there will be some tiny fragments of that collection of differential equations which are not closed, but which become closed after multiplying by an integrating factor mu, which only depends on x. And those are the ones where m of y minus n of x over n is a function of x. Maybe this is like a corollary. Corollary, if m of y minus n of x over n is just a function of x, then there exists mu of x such that mu m plus mu n y prime is closed, and therefore exact on a rectangle. Any question here? Yes?
Can you move the page up, please?
Oh, yep. I thought it would be visible. Is this visible right now? The bottom?
Yeah.
Would m with respect to what, like that in the corollary that first, yeah, would that always be a function of x, or is that?
Absolutely not. It's going to be extremely rare that this expression is, that any of these things are just a function of x. M of y is probably a function of x and y. N of x is probably a function of x and y. And n is a function of x and y. And there is some tiny, tiny collection of times when by some miracle, this function is just a function of x, and all the y dependency kind of cancels out.
So even if we find a mu that's only a function of x, it's still like highly unlikely that that's going to help us.
If you find, so it's kind of the other way. It's very hard to find a general mu that does the trick. And in some cases, there might not be a mu that does the trick. Next question is that we reduced our sites considerably and say, we could probably find a mu. We could actually like write down a mu that worked if mu was only a function of x, because then we'd only be solving a separable differential equation involving mu and x. And so then we calculated, when is it the case that a mu that works only depends on x? And that is if this condition is satisfied. If m of y minus n of x over n is just a function of x, then we can find a mu, an integrating factor which works, and we can explicitly write it down because it's only a function of x. So we're dealing with separable differential equations that we can actually solve.
Okay, that makes sense. Thank you.
Yep. Kind of a long and twisty chain of interdependencies. Yeah, so here's an example. We've got 4 minutes to do this. So the example is, and one thing that I should remark is that if you're a solution to where should I go? Let's say that this, after you multiply by the integrating factor, that this is actually a closed differential equation. So there exists a psi whose derivative with respect to x is this function, whose derivative with respect to y is this function. It turns out that the implicit solutions of psi also solve our original differential equation. So a solution here will give us a solution here. So we would actually be getting solutions to our original differential equation. Okay. Probably you won't have time to actually do this example, but I would like for you to do this as homework, even though I won't collect it because it's valuable. So show that, or really, this should be solve the differential equation x squared y cubed plus x times 1 plus y squared, y prime is equal to 0. And the first question that I will ask you is this differential form, or is this differential equation closed?
No.
This is not closed but calculate m of y minus n of x over m. And tell me what this is. And the answer should be, this will be equal to 1 over x. Thus, so I'm like doing bullets of how you should solve this problem because you don't have time. It's not closed, but this expression is just a function of x. Thus, we can write down d mu over dx is equal to 1 over x mu. This is separable, so we can solve. And what you find at the end is that mu of x equals x works as an integrating factor. So these are the bullets that you should follow to solve this differential equation. And time is just about up. So yeah. Any questions on this?
Are you holding office hours after this?
Yeah, give me about 5 minutes and then I'll come back around 1:05 and try to answer your questions.
Okay.
All right, have a lovely Friday afternoon and evening. Have a nice weekend. And thanks for coming to class.
Thank you.
Thank you.
So long.
Thank you.
started not until 2 technically. I'll be done before that.
While we're waiting for him, has anyone done question 2 on the most recent homework?
You mean the one just released this morning?
Yes. Sorry, I was muted.
No, I haven't done that one. Sorry.
Wow, lots of people in office hours today. So what's up?
So I have a question about maybe if we could possibly either do an example of one of these exact equations with an IVP, because there was one on the homework that I feel like I did it right, but then I literally couldn't figure out how to put it in terms of why, like the software wanted, so I figured maybe I'd done something wrong with the calculus somewhere.
Yeah, so I probably admit that can be really tricky. Like, in general, for an arbitrarily difficult equation, I have no expectation that I'll be able to actually write it locally as a function explicitly. But if they did it in the homework, then it's probably doable for the specific equation that was there. So let me see if there's something that I can do here.
Well, I mean, you don't have to work out an entire problem. Can we just confirm that maybe like what you're supposed to do is we solve it like we did in class today until the point where we get it to where it equals C?
Yes,
And
that's right.
We literally just substitute in X and Y with the point that they gave us and solve for C.
That's correct, exactly.
Okay.
So those two things are correct. That'll get you your full equation where the only things that are involved are X's, Y's, and actual numbers, right?
Right.
And then to actually solve that, you want to get Y on one side and have only X's on the other side, which could be quite difficult.
Okay. Well, I mean, I don't want to waste other people's time with you solving that because I do think I basically understand that. I think it might just be an algebra issue for me.
Okay, I'm happy to go over a particular example, but there do seem to be a lot of people who want to ask questions. But yeah, I'm happy to return to that and do an actual example if you'd like.
Okay, well, we can wait. Someone else can go.
I had a really quick question.
Okay.
So one of the homework questions, I forget which one it was on, it was talking about like a differential equation being homogeneous, and there was like a really unique way to solve it, and I was wondering if we had to know how to do that for the exam.
The answer is essentially no.
Okay. Okay, thank you.
I haven't discussed it, so no. We will, but any other questions? Any other questions? Obviously, there are a lot of other questions.
Are you gonna ask us to draw graphs on the exam?